Hello again. So the usual procedure. My name is Kai Hackbart. I'm with Bosch Software Innovations. I'm also in the board of directors of the OSGi Alliance. What did I want to say? T-shirts, exactly, T-shirts. So we have T-shirts for our 20th anniversary. If you don't have one yet, you can get them downstairs. Also socks. And then one more note, we have various banners around the facility where we describe use cases that different member companies have realized. If you're interested in this, just check them out. One is over there in the exhibition area and another one is downstairs, and I think there are one, two more. And with this, I hand over to Tim, who is telling us about his research he's doing with robots.
Thank you, Guy. So, my name is Verbelen. I'm an OSGi enthusiast. I've been involved in the OSGi Alliance for quite some years now as an invited researcher. But my day job is actually doing research, and I work with robots and particularly trying to learn them stuff. So we use all kind of mainly deep learning techniques to try to make them do stuff. But still, to integrate this robot with all the sensors and stuff, I still try to use OSGi because it's just a great technology for that, and that's what I'm going to talk about today. So, this is my robot. It's a Franca robot, and one of the nice things about this robot is that it actually has force torque sensors, so it can sense any external force being applied to it, which makes sure that if you, for example, if you bump into it, it just stops, which is a lifesaver. It really takes down the deaths at our department. And what's also nice with these sensors is that they can actually sense you pushing the robot to a certain position, and it can kind of go with your movement. So you can basically take it by the hand and move it into any position you like. And that's basically the main selling point of these collaborative robots, that you can easily kind of teach them by demonstration. You just pick them and you program certain waypoints, and then you can repeat it. So for example, if you want to grasp like an object, like a simple block, you record the waypoints to grasp it, and then basically you can replay that. So then next time you want to pick this up, it works again, or no. So this is like the rookie mistake with using a collaborative robot to teach it something, is that you have to remember where you've put the thing that you were teaching, because else it just knows your position. It doesn't work. And that kind of sucks, right? So that's when we unboxed our robot, we tried it out, and it was like, oh. So what we did is like, yeah, can we just add like a camera so we can have some visual input to the robot, and then figure out a way to kind of fix this issue, that it can actually correct for this behavior. So our camera is an Intel RealSense sensor. And so basically you had to skip all the manufacturer software stack and just take control of our own. So basically we had our camera, we connected it to a NVIDIA Jetson board. It's kind of the Raspberry Pis for GPUs. It's like an embedded GPU board. And then this guy would send the controls to a robot to kind of control the robotic arm. So let's get starting then, and let's start with controlling the robot arm. So first thing we thought about is, yeah, if we want to make an OSGi service to control the robot arm, how would it look like? And you could think of an interface that says, okay, I want to move certain joint in a certain position, or I want to set positions for all the joints all at once, or maybe I want to have it move to a certain XYZ position in Cartesian coordinate space. So these are the kinds of things you want to do with your robot arm. But then the question is, when do I return in these methods? Do I wait until I've reached that position, or do I immediately return and you just have to do some sleeping until you're there, or you have to constantly poll for the sensor values to see when it's there? So it's not really an easy way to decide, basically. Fortunately, in OSGi we have a thing called promises. And with promises we can have the best of both worlds. So now we just return a promise, and the promise returns immediately after calling the method. So you call set positions, you immediately get your promise, and the robot starts moving. And the promise gets resolved whenever you're done, you reach that position. And if something happens, for example, if somebody bumps into the robot, it doesn't reach the position, it also resolves the promise, but then with an exception. So you have the nice behavior of the promises. You can call this asynchronously, but you don't have to wait for the robot to report its position or something. And this also has a nice effect that you can easily chain kind of movements together. So for example, if I want to let my arm do something, I can say, okay, arm.open gripper, and then use the then with the lambda to chain them nicely together. So I can say, okay, then you move to a certain position, and then I want to turn one of the joints, and then I want to move to another position, and then I close the gripper. So this is basically programmed the sequence that you saw in the beginning. And even this chain immediately returns a promise, and it will resolve when all the steps are done. And if something happens, if you bump into something, then the promise will give you the exception. So cool. So now we can have our arm, we can control it with a nice service API. So what about the camera? How will we access the camera? So we do the same exercise. So let's come up with an interface for our camera. So these things, what you want to do with the camera, you want to get a frame from it. So you could say, okay, I have my camera, and I just make an interface that says, give me a frame. But yeah, typically your camera is like at a certain rate, a certain number of frames per second, it just produces frames. So it makes more sense to just listen for the camera and say, hit me whenever you have a frame. So you could say like, yeah, I want a listener, I register it, and then the camera will push me the frames, but then you lose kind of the concept of what is the camera. So again, you have like two approaches, but you really want to have like both, really. That would be awesome. And of course, in OSGi, we have something for that. So if you think about the Java Stream API, which they added in Java 8, they added this nice thing where you can call stream on something. So if you have a collection, like a list, you can stream it, and then you can have these mapping and filtering and counting and all these nice operations. And that's really cool. So could we have something for our camera that you can also say, I have my camera and I want to stream it, and then I have some lambdas to kind of process the whole thing. And that was basically the idea of OSGi PushStreams. So in a push stream, similar to the Java 8 streams that iterate over collection, here you also iterate, but you iterate over stuff that still has to come in. So it's totally asynchronous, but the API is kind of very similar. So now your guest becomes a push stream, and as your guests reply, you can process them, and at a certain point in time you count them and you have your result. And again, here we use the promise. So for example, whenever you start waiting for your guests to reply, you immediately get a promise to the result, and this will resolve whenever all the guests have replied or you close down your list, for example. And this is the same concept that we can then use for our camera. So we use our camera now has a stream method, and it gives us a push stream of frames, which means that we can start streaming, and then we can, for example, have a map operation to process all the frames nicely. But of course, yeah, how do we process our frames? For that, we use a neural network. And marketing guys call this AI. Basically, what it is just a data-hungry pattern recognition. So you just give it lots and lots of images, and it kind of learns some structure in these things and reproduces it. So I deliberately took that picture because for any human being, this is clearly not a cat, but for a neural network, it will be, because it has lots of the patterns that are typically there for a cat, although it has no physical representation of a cat, it just recognizes the patterns. But still, for us, this is good enough, because basically, you just want to spot some patterns in the image and then go towards that position. So then we can put everything together. So now we say, okay, I want to grasp. So instead of just replaying the recorded positions, I now have my camera, I start streaming. I don't want to wait forever until I see something, so I put a timeout on that, and I start mapping all the frames. And every frame is forwarded through a neural network, and whatever comes out to neural network I use to update my controller for the arm. And whenever the controller says I'm done, I short circuit and I resolve the promise with the Boolean, whether I was able to grasp anything or not. So all good, but how do you train this neural net? I mean, it's magic, and it really isn't. So basically what we wanted to do is, remember me taking the robot by the hand and doing the demonstration, and we found it was crucial that you, with neural nets, you typically need lots and lots of data, and you need to label them and all this hassle. And for us, the key issue was that we really wanted to have like this single demonstration is all you have, basically, and you have to try to come up with something with just that. So let's look again what the robot sees during this demonstration. So here you can see the robot's view, and basically the key point is at this position where you just hover the object, where your object is nicely in the center of your camera frame, and this typically always happens because the operator will always reach to the object and then go down to grasp it. It's kind of the standard way of doing it. So we make the assumption that at the point in time that you reach it, your object will be somewhere in the center, and this is basically the information that we exploit. Because if you have another frame where your object is somewhere else, we just try to find the best matching pattern, basically. So in this case, this is here, and so what you want to know is basically the vector you have to move towards the object, and also the angle in which you have to rotate in order to have the same thing as during the demonstration. And if you see the same thing, then you're probably good to grasp. But now we still need enough data to feed through a neural net for the training. So basically the trick we do there is we generate it. So we have this one frame, and from this one frame we make a center crop of the thing we want to detect, and that we will rotate all over the place, and we also adjust the brightness a bit, so we can create an endless stream of images that resemble the stuff you want to pick up. And similarly, we can take crops of other places in the image or even other images, we don't care, and these are things you don't want to care about. And so this way you can easily generate from this one data frame lots and lots of samples to quickly fit a neural net. Yeah, so that's because we randomly crop them. For the positive, it's like within I think few pixels that we can shift, but anything bigger is negative. So this is probably a shift of like 2-3 pixels too far to be positive. So then it kind of resembles the real thing, but it's like these ones are like on the boundary of it. Yeah. Yeah, so we have both the notion of is it the object or not, and also we try to regress the angle if we spot it. So the neural network basically has an activation on the object is here and an estimation of the angle, so how to rotate. Yeah. Any other questions? No. Okay. So one of the problems was that this Jetson board is perfectly fine to process the camera frames, but not really for training on the dataset because it has very limited memory. So basically what we did is, okay, no problem, let's just train on a GPU server we have in our data center. And then typically this is a huge hassle to kind of configure everything and make a REST endpoint or whatever to have something remote available and all these things. But with OSGi, it's actually just plain and simple. You just use a remote service and you deploy it there and you're done. So this is actually one of the nice side effects of using OSGi, that you can just use your bundles, and if you have a different deployment setup, you just take your bundles and put them wherever the best fit is. So this is one of the nice things. But then, of course, the question is, can we now pick up the block? Well, yes. So now the camera constantly pushes his frames at 30 frames per second through the Jetson, processes the frame, and comes up with a vector and an angle to pick it up. And also, if there's other objects around, it will just see it and look for the correct one. And because it's a closed loop control, you're constantly processing all the frames. You can even have it move around, and it will just follow around until it stands still and it can pick it up. Now you would think, yeah, this is pretty easy. I could come up with like 10 lines of code to process an image to find some blue blob in an image, so what's the big deal here? But the thing is, with the neural net, you basically can feed it anything, so you can teach it on any object and it will kind of learn it. So we can use a tape, or we can use a screwdriver, or we basically threw all our office supplies at it. And yeah, that's the cool part. You can just use it to pick up anything. And every single one of them, we only just show it once, and then it learns how to pick it up. Yeah. Yes? The height, we use it from the demonstration. So once you are at a similar position, we keep the height fixed. We move around, and then the actual grasping is the same one as you used during the demonstration. So so the height has to be the same. It has to be the same object basically. Yeah, but for each object you give one demonstration.
Oh, I see.
Yeah, yeah, exactly. So this was it. Thank you. I also would like to thank Tim Ward for the Promises and PushStreams specs. He put a lot of effort in there, and also my colleagues for feeding the robots and keeping them alive. So thank you very much.